They've also got to interact with KUKA robots from KUKA systems, and they've got to learn the ins and outs, how to get started with the KUKA, how to get started programming, and even how to integrate ROS2 to work with KUKA. So we hope this and many other initiatives will help these learners or TVET and university students take their skills to the next level, and to some point also contribute to them being plug and play to the industry.
My name is Lenny Anna, and I'm going to be taking you through this KUKA robot arm. And just before I get into it, I'd like to talk about myself a bit. I studied control and instrumentation, graduated in June this year, and for my final year project, I worked on this robot arm, and I'll be showing you what went into that project. I also have been participating in Robotics Dojo competitions since they began in 2022 and earlier on in different avenues. I then went on to join the Robotics Dojo training program and eventually became a robotics trainer. I currently work part-time with Afriport Robotics and Robotics Dojo, and I recently, starting this year, started working as a Robotics Dojo research member. This is the KUKA Agilus KR6. There are various classes of robots. KUKA is a company behind this robot. And just as we have different phone brands, we also do have different robotics manufacturers. This robot was purchased as an industrial robot arm that was specified for research here in JKUAT University. It has a 6 kilogram payload, which means it can only lift things that are up to 6 kilograms. Some of you, when we interacted earlier on, said 6 kilograms is rather little because you're used to industrial robot arms that lift cars and lift chairs and very heavy objects. But 6 kilograms is very much enough and adequate for certain applications. And I will also show you some of these applications that can be performed on this robot arm. And we'll make sense of why 6 kgs is actually more than you will need for an industrial application. So, given that this is an industrial robot arm, there are various challenges moving from the casual robotics that we are used to, the ones where you program your own microcontrollers and single board computers such as Raspberry Pi. The moment you make that bridge from I'd say, casual robotics into industrial robotics, you come across multiple challenges, most of which are never mentioned even in our lectures in classes. And some of these challenges are access to resources. Industrial robot arms are usually closed source, and since they are a commercial avenue, the manufacturers tend to stay put with their information. But there is also another reason as to why resources around this are limited. Around that is very big and enables you to have this vast resource pool in terms of getting up to speed with whatever application you're building around. So this is one of the main challenges that I also face with this robot arm. The other thing is portability. We might not think about it, but whenever you're working on a robot, you have the ability to work from the labs, and later on in the evening, you can take it at home and continue on testing your code. But this is limited to the facility where it is installed. We had to carry it from where it is installed this morning for this demonstration, but it lives in the IP labs, and you have to work with it from there. So that gives you a limited flexibility in terms of how and where you can work on it. The other challenge is the control systems. Very advanced, very demanding, and some of the times, one of the places where you get stuck is actually controlling this robot. When you are building robot arms here, last year's robotics video competition did have a robot arm that you are able to use to pick objects around. And one thing that is different from that is that this robot also comes with brakes. So every single joint has a brake pad, similar to brakes in vehicles. And that means anytime it's not in use, the brakes are engaged. So right from that, there are multiple interfaces that you have to keep thinking about. You have to keep thinking about the sensors attached to each joint. You have to think about the brakes, for example, the amount of current running through it. So the control systems around this are very complicated, but luckily there is a solution to this, and the solution is partially what I worked on. The other thing is safety. This robot is 50 kilograms in weight, and that means if you are working with it, there are various hazards such as pinching. If you work too close to it and send the wrong command, it can fall on you and badly hurt you. So you have to be careful around working with it. The other challenge is versatility. They're usually programmed to do one task, and that means whenever you want it to perform other tasks, you're going to have to rethink the entire programming infrastructure, which becomes a problem. The other challenge, which I actually directly solved and I'm happy about, is integration. When you talk about integration, I mean integrating this with other systems. You might want to add a camera so that the robot moves around the workspace and looks around and is able to grab objects. But for you to build that interface between the camera and this, there are various challenges that make that almost impossible. So today I'm going to be talking about, I'll demonstrate a bit how we currently the robot, and that is by using this teach pendant. There are many other ways of controlling it, but this is the most accessible way. And you get access to everything. The safety switches, the brakes, the actual, you can change the speed of the robot that it moves on. And I can do a small demonstration, which may be difficult given that I am holding the microphone, but I'll just demonstrate how the various axes. It has 6 axes, so I'm going to move through all the 6 axes. Axes you can think about as joints. Most of you in the engineering classes have taken a class on this, so you'll be able to see it practically. And I will begin now. Okay, so before you start working on the robot, you have to activate you have to release the brakes, which is what I've done by pressing on the levers at the back. There are also emergency stops that we have access to in this arm. And I will start by moving the first axis, as you can see. That is the base joint, axis 1, and then we have axis 2, which we also call the shoulder joint. We have axis 3, the elbow, and you can think about it similar to how you think about your human arm. That is how they have labeled. We also have the wrist joint. This is the forearm. And then at the wrist, we have access to this, and you can also rotate. So I will move the robot towards a direction so that you can see what I mean. Right now I'm moving it at a manageable speed so that I do not accidentally move it to an unwanted location. Now once it is facing you, I can show you the rotation of the tool point, which is the final and 6th axis. So if you have a tool point here, you can be able to work on it and change the various orientation that the robot is currently positioned. So I will put it in an upright position because the next demonstration is going to be the program that automates all of this, and it's going to be interesting to see how it moves from that position to its home position and the various other programmed example coordinates. Okay, so I will stop with that for now and go on to the rest of the presentation where you will see the actual solution that I worked on. Thank you. The diagram is simple enough, but trust me when I tell you there's a lot of work that went in the middle. So we do have the robot, and this is the robot arm. It is connected to this box down here. This is its controller. Think about this as its Arduino or its Raspberry Pi. It is gigantic. Runs Windows 10 IoT, which is a stripped down version of Windows 10 that is custom for this application. And the teach pendant is your control access to this robot. For you to be able to connect to the robot, you use Ethernet, which is what I'm connected to with my laptop. And I'm going to show you the program. It might not make sense looking at the screen, but I'll show you a visualization. So the first thing that was a challenge is, even though I'm connected through Ethernet, I still cannot read the actual joint sets. So the first objective that I had in my research project was building a way to read from the robot's joint coordinate space. And I did that using a protocol that was developed by an open source community, so I built my work on top of that protocol called AVP, and I'm reading directly from the robot's memory space, and I can be able to visualize the arm. So this was step one. I'm able to visualize it, and as I move it, you should be able to see the live demonstration. Now the second bit was being able to write your own program and send it to the robot, which was non-existent at this point. So based on what other robots here have been built on, that is the ROS, or the Robot Operating System. We have presenters here that will take you through ROS. So I will not go into depth about that, but I wrote two programs. The first program listens to any other program that is publishing information about the coordinates. And then the second program is a simulation program that runs demo coordinates. So I will run the coordinates, and it's now actually sending the coordinates to the robot, but the robot is not moving. And that is because of some of the safety features that were built into this robot. So for me to be able to make the program work, I have to release the brakes and allow it to start running. So right now it's running my program, which I had put in some demo positions. So right now it's going to 6 demo coordinate spaces that I had programmed, and it is being piped through the control interface that I developed. And now this gives you access to the robot's entire system, meaning that whatever application you build around that, you can use the control interface that we developed since we open sourced it, and you can be able to build your own applications around this. I will leave it at that and show you some of the other ongoing research projects around this arm. So once we were able to get access, programmatic access to the robot arm, this enabled us to go into different research projects. And one such research project is visual surveying. What we mean by visual surveying is the ability to integrate a camera with the robot. So you can imagine if you have an application around, let's say, pick and place, you can program into the system that once you see these red objects, pick them and place them in the blue box, or whatever application you have around that. And there are special cameras that we have access to at Robotics Dojo. And the one that you can see at the bottom there that was in the slide, you'll see, is called Intel RealSense Depth Camera. And the difference from a normal camera, so I'll show you the RGB interface. This is what you're used to from a normal camera. But you have access to something called the depth information. And depth simply refers to the distance to the object. So in a regular camera, you cannot tell the distance to an object, but with a depth camera, you have access to the depth map that enables you to gauge distances to objects. So this is important for robotics applications so that you cannot collide into objects. The blue color shows objects that are close, the red color shows objects that are far away, and black means it's out of range of the depth sensor. One of the other applications around visual surveying is safety. So having a camera in the workspace can be able to make the arm safer in that whenever a human walks into the workspace, you can either change the trajectory of the robot arm or you can stop it if it is in collision with the person in the workspace. This is another research project that is currently ongoing at the Robotics Dojo Research Group, and is wire additive manufacturing. So some of you might be familiar with 3D printing, where you create your models, put them in a printer, and it's able to melt down some plastic and form it into a part, a physical part. So in this case, we are using metal 3D printing. We are able to put a wire, melt it down, and basically do the same thing that a 3D printer does. But given that this is an arm, we have access to more degrees of freedom. At JPOT, we do have a program called the Nabuja Project, where they build rockets, and the end goal is to be able to launch nanosatellites into space. And for us to get there, we do need to build more complex engines, liquid engines, and these liquid engines get very complicated to fabricate. So this is one application that can go directly into one of the other projects that are currently ongoing in JPAD. These are other applications. Again, I try to find applications that are in line with what we do at the Jomo University. We do manufacture the Taifa laptops. Some of you use them. Most of you, I can see, are using different ones. I don't know why you not use laptops from your university. But this kind of robot arm can be embedded with tools such as PCB assemblers and PCB soldering equipment, so that we'll be able to fast-track manufacturing processes. We are also very good here at JPAT with agriculture, and so there are other research projects focused on agricultural use cases, particularly in the lab setup where we want to test maybe different types of seeds and how they perform to different environmental conditions. The other thing is also in packaging in the food industry. This is just another application that can be used with this arm. We've just begun to work with this arm, and so there's a lot going on, and we are actually looking for more students to actively engage us in developing projects around this industrial arm. Thank you. That will be my presentation. We can have the questions later after the program.
Dr. Engineer Dorito, for your remarks. We want to have a blended approach so that we have a bit of this and a bit of what happened in the morning. But before then, we would wish to have a review by our judges. We'll have 5 minutes each of our judges giving reviews after what happened in the morning, so that we know probably where things were going right, where they were going wrong, and they will tell us what they saw. After that, we'll probably have one presentation. Then we'll give you the floor after that. So at this juncture, we put our hands together and invite Professor Sakaguchi to come and give this review.
Good afternoon.
Good afternoon.
First of all, I'm very impressed about your work during this product Dojo week. So the day before yesterday, I got a technical presentation from all of this team, and every team assembled all of the devices. Not only Arduino, Raspberry Pi, you successfully installed this LiDAR system, and your concept is very clear. So it was very nice to hear this kind of aggressive work. And second of all, so today, so you are expecting more interesting game today, but you found some issues, maybe Wi-Fi. So this is not expected before. Yesterday, your machine, your robot, was working well. So you are also expected today, but it happened, these issues. But don't mind. So this kind of issues can solve in next time. So if you can solve next time, no problem at all. So, and moreover, I'm impressed about your teamwork. So when you met this kind of issues, so every team started to discuss and try to solve. So I found a good teamwork today. So this is a very impressive point. And finally, I'm proud of again to this attending team, and thank you very much for your good, aggressive passion and nice work. Thank you very much.